Okay, we're going to continue on here. We're chapter 12ing, I think. And we got into officially alcohols, I think, last time. Remember, alcohols have the functional group of the OH group, which is a polar group. Um, Remember that when we do name alcohols, they do end in OL at the end of it. Also based on the number of carbons. You're looking for, again, the longest carbon chain that has the OH group attached to it. Also, around three or more carbons in an alcohol, you do have to give the location of where that OH group is. Again, if we had something like this, this is three carbons, which is based off of propane. Since it is an alcohol, it'll be propanol. We would have to give the location of that, and it's at carbon number 2. So again, that would be 2-propanol, which again is our location of our OH group. Remember, in terms of numbering, the OH group takes the priority, so you want to give that functional group. Just in general, you usually want to give the functional group the smallest number as you do it. Once you lock in that numbering, any other groups that are attached are numbered accordingly, and you put your groups in alphabetical order. We talked about primary, secondary, and tertiary alcohols and reactions that they undergo. Again, if you have a primary alcohol, and that basically means it is an alcohol that has the carbon that has the OH group on it attached to one other carbon. And if we do a primary alcohol here and we oxidize it, as we talked about, again, this oxidation is the removal of two hydrogens. We always take the hydrogen that's attached to the oxygen, and we take one of the hydrogens that are attached to the carbon that's attached to the oxygen. And as we talked a lot about, nothing much changes other than we're going to remove those hydrogens. And we do need to insert a double bond there where our carbon oxygen is. That will give us H2 that comes off. This gives us, again, an aldehyde. And an aldehyde has this part right here as its functional group, carbon, oxygen, double bond, H. As we also talked about, you can oxidize the aldehyde one more time. And this sort of second oxidation, oversimplified, but basically what happens is we're going to insert an oxygen there is what's going to end up happening. And again, that is the two sort of definitions of oxidation, either gaining oxygen or losing hydrogen, and those both basically demonstrate that. This makes, again, another type of organic compound, which is a carboxylic acid, which has this right here as its functional group. So that is the functional group there with carboxylic acid. If we take a secondary alcohol, actually, yeah, that's all right. So here, if we take a secondary alcohol, once again, this carbon has two carbons directly attached to it that has the OH group. And if we oxidize it, same idea, we're going to remove the H2, which is those two hydrogens right there. Everything else will basically be the same. And I'll just draw it the way it was. It's fine. And we'll put a double bond right there. And this is going to create a organic group known as a ketone. And the ketone is basically a 3-carbon run where you got a carbon oxygen double bond in the middle of the 3-carbon run. And that is like right here, 3 carbons in a row. And on the middle carbon, we have our double bonded. Here, if you oxidize our ketone again, nothing's going to happen. And lastly, if we had a tertiary alcohol, which again would have obviously 3 carbons attached to that OH carbon. And in this case, we have a tertiary alcohol. Once again, will not go through oxidation. again, because it is missing that kind of second hydrogen that's necessary on that carbon. So you only have one basically you can remove, not two. So we'll not go through it. We finished up talking last time about some reverse sort of reactions that occur. And those are the reduction reactions. So if you head in this direction here, that's the reduction reaction. If you go in that way, reduction will get back your alcohol. And if you do the reduction, it will get back your secondary alcohol if you started with your ketone. Reduction reactions basically just putting the hydrogen back on, basically, except for the carboxylic acid, we're removing the oxygen and then taking the hydrogens and putting them back on as we go through there. As we talked about at the end there, the hydrogens come on just like they kind of do when you have a carbon-carbon double bond. It comes on at the double bond between the carbon and the oxygen if you're going in the reduction way. And again, make a single bond hydrogen onto each of them. Will get you back to your original things. Any questions on alcohols? Yes. Why was it say again? Why is the CH3 on the? On which one are we talking about? I'm sorry. Here or was on the very very top? Uh, right here and what do you want to know about it? On the right hand side. Why is it here? uh, yeah. So if we're talking about sort of the connection between these, it is carbon to carbon connection, even though it's written as CH3. It's not the hydrogen to carbon connection, if that's what you're asking. I don't know if that's what you're asking or not. But this CH3, nothing happens to it. The only thing that happens is we're going to remove these hydrogens. And again, I'm going to make that double bond right there. And everything else will stay the same. But remember, when do you see things written sort of in kind of sort of in condensed formula, if you will? The connection here is carbons to carbons, and then the hydrogens are on the outside. Obviously, I have some more stuff there in the middle that should be there, but that's sort of the connection as to how it is, if that's sort of what your question was. Yeah. Other questions? Got it. All right, let's continue on then. Methanol, as you can see here, is our first oxidation. We're going to remove our hydrogens and make our aldehyde to make methanal Al, which is an aldehyde. And again, one more oxidation, put it in that oxygen there, making methanoic acid, which is again a carboxylic acid. Ethanol, again, same idea. You can see here we got our oxidation, making our aldehyde, and breaking it down to CO2 and water at the end through sort of fermentation. Now, let's talk about the next sort of group, which is thiols. And thiols are similar to alcohols, except they have the functional group of a sulfur involved, so an SH. So that is the functional group of a thiol. Because they do contain sulfur, they usually don't smell so good, which I imagine why we see the skunk up there. And they usually have pretty strong sort of smell. They actually put sulfur like in gas line, so you can actually smell it if it's leaking. Um, the good news about thiols is you need to know the functional group, and you pretty much just need to know none of that. But you do need to know a reaction that the thiols undergo. So let's talk a little about a reaction that they undergo. So if you have a thiol, and it doesn't really matter sort of which one you got going on. And you take two thiols together here. Let's do a short one here, maybe. And if you do a oxidation of two thiols, what's going to happen is very similar to what happens with alcohols, which is we are going to remove our hydrogens. So we're going to remove a hydrogen here, and we're going to remove a hydrogen here. And sometimes it's good to kind of draw them back to back like that. So these two are going to come off, and that's going to make H2 on this side. Then what basically happens at this point is you just kind of squeeze both parts together. So you just kind of put them together, and they're going to attach through the sulfurs. And again, nothing else changes here, so you could just go straight off and copy CH3, CH2, CH2, and an S. Once again, we remove that, so we're going to pick back up on the other side here. And that is always the connection that occurs here when you put two thiols together. This makes a disulfide bond, or bridge, it is sometimes referred to. There's an amino acid, cysteine, that has sulfur in it and makes this disulfide bond or disulfide bridge. So if you take any two thiols and put them together, you'll remove an H from each of them and basically connect both of them together through the two sulfurs. And again, nothing else changes. Just like anything else, we could also do a reduction of sort of a disulfide bond. So if we had already have done this, and say we had something like this, and we add some hydrogen, which basically is going to do the reduction reaction. And the reduction reaction here is going to happen just like we kind of take off the hydrogens. It's going to happen right there, always between the two sulfurs, is how they're going to break back apart. So what we're going to essentially do here is just break back apart these guys into two separate molecules. So if I was doing this, I would just copy one here to the left. And obviously the other one will start with the sulfur to the right. And basically each one gets a hydrogen to kind of get you back to your thiol. So just going to bless you, just going to pop a hydrogen on both of those. And now we get back our thiols basically here. So if you take two thiols with the sulfur group on there, again, if you go through oxidation, you're going to make this disulfide bond or bridge, which is just bridging those two sulfurs together. If you already have sort of a disulfide bond or bridge made already, and you add hydrogen to it, it's just going to break it back into the individual thiols, basically. And each one will just get a hydrogen, break it always at the sulfur-sulfur bond. Any questions on that there? Yeah. Exactly, Cheryl. I'll circle it because it's not letting me choose different colors. So this is basically where we added the hydrogen, one to each of them, and we broke this guy right here. So that part comes off, and at the end, where the sulfur is, each one gets a hydrogen on each one. Yeah. And it's basically opposite of what we did up here in the oxidation step, where we removed a hydrogen from each and then just kind of squished them together. Here, we're just basically breaking it back apart. Yeah. Other questions? All right, so for thiols, you need to know the functional group is the SH. You need to know those two reactions. You don't need to know how to name them or anything like that for those guys. Let's then talk about ethers, which is another organic compound. And the ethers have a functional group of carbon, oxygen, carbon. So here we have sort of an oxygen inserted in between two carbons is the functional part of it. And the way we're going to name ethers is we're going to take more of the common name approach to it rather than the systematic sort of name of it, or the IUPAC name. So the common name approach to these guys is pretty simple. All you want to do is look at the oxygen and then basically just look to the left and to the right and find what carbon groups are hanging out there. So if we look to the left, we have a one carbon group, which is a methyl group. Over here, we have a one carbon group, which is also a methyl group. And just like anytime we have more than one in the same group, we do add a prefix. So the common name for this is dimethyl methyl, and then you simply just put ether at the end of the name. So just dimethyl ether. Now, if you had two groups that were different, you go alphabetical on the group. So alphabetically, just name the two groups, and then just again put ether at the end of it. So we're gonna go with the common names for ethers. Much easier than the formal name, I think. So if we had something like this, what would this one be called? Yeah, so again, we want to we could recognize hopefully our ether by this row here of carbon, oxygen, carbon. So again, that is the functional part of it. And once you do, if you want to do the common name, you could just kind of box out the oxygen. And when we go to the left there, we do have a methyl group. Here we have a two carbon group, which is a ethyl group. And as you said there, and as we were talking about alphabetical order, we'll put the ethyl first, methyl, and then again, you're just simply going to put ether at the end of it. Yeah. Any questions on that there? Right. So here's another example. Once again, there's our carbon, oxygen, carbon, which is the ether part of the compound. If we just want to isolate the oxygen, to the right there's a three carbon group, which is a propyl group. To the left, again, our one carbon group, which is our methyl group. And again, put it in alphabetical order, M before P. We have methyl, propyl, and again, an ether in this case. Now, if you had to draw it, let's just say you had to draw ethyl pentyl ether. Why don't you take a moment and see what you come up with? I want to work backwards. So as soon as you see ether in your head, you should hopefully understand the functional group, which is this. And I would say that if you are drawing an ether and you can recognize it obviously as an ether because it says ether, I personally would just start with an oxygen. And because that's going to be kind of like your center point here of your ether. And then I really just kind of go through these one by one and figure out how many carbons I need, right? So if I have a pentyl, pentyl is based off of pentane, which is five carbons. So, and really, since you're drawing it, it's your call. You can put the five on either side. I probably should have went the other side, so I just tried to squeeze it in there. And then ethyl is based off of ethane, which is two. So we lay up some two carbons at this point. And just like anything else at this point, really everything else is just going to be hydrogens. So we'll need three hydrogens there. We'll need two there. We'll need two there. We'll need two there. Two there. Two there. And three at the end. So we'll end up with CH3, CH2O, CH2, 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 and CH3. So it should have three, four, five carbons on one side and two carbons on the other. Yeah. Any questions on that? So sometimes this one's a good one. They kind of just start in the middle with the oxygen. And since we're kind of basically using common names, you'll basically have the group and carbons that you need to put on each side and fill in their hydrogens like normal. Any questions on that? Yeah, if you're going to do the line, you could still do the same thing. I would start with the oxygen in the middle because you do need to draw it, right? And then same idea, you could just draw your appropriate lines, which would be there's one, two, three, four, and five, and then one and two, so something like that. Yeah, that would be as well. Other questions? All right, so one of the things ethers are used for, put you to sleep, right? And over the years, they have replaced some of the hydrogens with some fluorines, which has been less volatile, less flammable, and maybe some less sort of side reactions. But again, that's usually used to kind of put you to sleep if you're doing something. All right, so let's draw a couple of these structures here: 3-pentanol, ethanol, diethyl ether. Let's do. Let's do a butyl ethyl ether as well. Okay, so let's take a look, see how we're doing. So once again, starting backwards, first off, first key is OL, which tells me is what type of compound. It is a alcohol, right? And pentane part tells me 5 carbons, right? So that's what I'm gonna do. That's 5, I think. Now 3-pentanol tells me the OH group's not carbon number 3. And again, because you're drawing, you could go either way. And actually, in this case, it doesn't really matter which way you go. That's going to put the OH right about there. At this point, we're pretty much out of the name, so we're just going to put in some hydrogens here. Need 3, need 2. Here, we just need 1. We need 2, and we need 3 in this case. Any questions on that there? Again, same idea if you're doing more of a line structure, 1, 2, 3, 4, and 5, and a OH right about there. Yeah, that should be good. Same deal here. OL tells us it's an alcohol. Ethane tells us it's 2 carbons. So that's not too bad. And now we just basically fill in are hydrogens, and we do need to put the OH, otherwise it's not an alcohol. And it could actually go on either carbon because they're both going to be carbon number 1. Doesn't really matter where you put it. So you could go left, you go right. You do need to adjust the hydrogens on the one that gets the OH here, right? So it just needs 2 in this case. Here for diethyl ether, once again, ethers are carbon, oxygen, carbon. So if you're going to draw it, once again, I would start with the oxygen kind of in the middle. And now we can see diethyl means we have 2 ethyl groups. So those are two carbon groups, one on each side. And that is what we will throw in. And at this point, we're ready to just add hydrogens. So I need 3 there, I need 2 there. 2 there, and 3 there. And once again, if you're doing sort of line structure, I would start with the O and then 1 and 2 and 1 and 2. Remember that when you're doing this, that right there or that right there is not a carbon, right? Because they're attached to the oxygen. So the first carbon is here and the second is there. First one, and then the second is right there. Yeah, so again, because that's an oxygen, that's not a carbon, obviously, at that point. Question on that one there. Last one here, butyl ethyl ether. So again, I'm going to start with the oxygen. And ethyl is a 2-carbon group. So we'll just do 2 carbons. And butyl is a 4-carbon group based off of butane. 1, 2, 3, and 4. So I try to squeeze it in there. And at this point, we can just put some hydrogen. So I need 3 there. I need 2. I need 2. I need 2. I need 2. And this guy here needs 3 in this case. So it basically CH3, CH2, CH2, CH2O, CH2, CH3, basically. Yeah. Same deal, line structure, start with the O and do a 1, 2, and a 1, 2, 3, and 4 coming out there without it joining the next guy next to it. Yeah. Any questions on any of those there? Okay. Let's see here. Let's talk a little bit about some properties of alcohol. We touched upon some of these. Obviously, we've touched upon primary, secondary, and tertiary. And again, when you're assigning that for alcohols, you're always interested in the carbon that's attached to the OH and how many carbons are directly attached to that carbon, giving your primary, secondary, tertiary. The importance of that, as we talked about earlier, in terms of reactions as to what type of oxidation reactions they may go through. Primary giving you an aldehyde, secondary giving you a ketone, and a tertiary, as we talked about, because it's lacking that second hydrogen, will not get any type of oxidation reaction occurring. So for each of these here, are they primary, secondary, tertiary? Take a second. We want to look at the carbon that's attached to the OH and how many carbons are directly attached to that. So that's 1 carbon, 2 carbons. This would be a secondary alcohol. Over here, this would be the carbon that's attached directly to the OH. And directly attached to that carbon is only one carbon, and this would be a primary alcohol. And lastly, this is the carbon that is attached to the OH, and directly attached to that is 1, 2, and 3, which would give us a tertiary alcohol. Any questions on any of those there? Okay. Yeah. It doesn't, because when you're assigning primary, secondary, tertiary, and you're looking at how many carbons, we're looking for how many carbons are directly bonded to it. So when we look at that, so we basically have that there, right? And these are all hydrogens in that case. So when we look at this carbon, it is only directly attached to that carbon. This carbon is directly attached to that carbon there. So we're looking for direct attachment, not like part of a chain or anything like that. No. Other questions? Yep. All right. One of the important properties of alcohols is its solubility, and it is really has to do a lot with alcohols having that OH group, and that OH group in alcohols is really the same OH group that you see in water. Water just has two of them, basically. And remember that when you have this situation, what's going to happen is you're going to create a really strong intermolecular force, which is known as hydrogen bonding. And this bond here is a polar bond, which means electrons are not shared equally. And the oxygen part of that bond in the alcohol is going to be more negative, and the hydrogen is going to be more positive. And that's exactly what happens in water, which is a polar molecule as well. The oxygen part of water is more negative, and really the hydrogen part is more positive. And how molecules interact with each other, again, is through intermolecular forces, which is essentially just a very simple interaction of the positive side of one molecule is attracted to the negative side of another. So what happens in this case is the positive side of, say, the alcohol is going to be attracted to the negative side of oxygen. And they're going to be able to do a really important intermolecular force, which is known as hydrogen bonding. And that's going to make alcohols really soluble in water. And they're going to be really soluble in water because they are like dissolves like. They're using similar types of forces. But there is a limit to the solubility, and it has to do with alcohols and really kind of the two parts of alcohols. When you look at an alcohol, say if we added some carbons here and hydrogens to this alcohol and make ethanol. This alcohol is basically two parts. It has a part that's basically all carbons and hydrogens, which is nonpolar. And what nonpolar means, if you remember, they share electrons equally. It's basically a neutral part of a molecule. There's no positive side or negative side. And it has this polar part up here, where the OH bond is. And because of that, again, it's able to interact well with water. But what happens when you get to bigger, say, alcohols that have a lot more carbons and hydrogens on this part of it, as the nonpolar part gets much bigger, the solubility starts to decrease and they're not going to be very soluble in each other, because what you end up having is, as you can see here, maybe on the bottom one, you have this really big part that is nonpolar, and you have just this little part that is polar that can interact with water. And what happens is what's referred to as steric hindrance. It's a fancy way of saying that big nonpolar part gets in the way of it being able for water to get in there and interact well with it. So usually around 5 or more carbons on an alcohol, you will see the solubility start to drop to nothing, because of that really big nonpolar part just gets really too big for it to interact well with water. Underneath that, though, is usually fairly good. If you got less than that many carbons on there, like something like ethanol or methanol, relatively small, that nonpolar part's not super big, doesn't kind of get in the way, and it allows everybody to interact well with water and be soluble in water. So, as I mentioned, typically you can see here, you're good with 1, 2, 3. When you get to 4, you're starting to get into a little bit of trouble. in terms of solubility because we're getting that nonpolar part too big. As you hit about 5 or more, you're in some super trouble. It's not going to be very, very soluble at all. Also, on the same note, if you have alcohols that have multiple OH groups in it, which you can, it's possible to have some alcohols that have multiple OH groups in it. That actually will increase the solubility because anywhere there's an OH group, it allows it to interact well with water and be soluble in it and mix. So if something's soluble, right, that means it will mix together and have no problems. And if it's insoluble, it will not mix. So about 4 or less carbons for alcohols, you're good in terms of solubility. Getting above that, you're going to start to run into some troubles in terms of solubility. And also ethers as well. Again, same idea with ethers. They will have some issues as well. Also, alcohols, because of that OH group, usually has very high boiling points and melting points. And that's because when a alcohol is with another alcohol such as itself, they will be able to hydrogen bond. And because that's a relatively strong attraction between them, that means that they typically will have a higher boiling point or melting point than other organic compounds. If you compare an alcohol to just an alkane, the alcohol here is going to have a much higher boiling point because it could hydrogen bond with itself versus an alkane, which is straight up nonpolar, no polar part to be found anywhere in there, is going to use the really weak dispersion force type of interaction. And that's like the weakest type of interaction you could have. And that means they typically have very low boiling points and very low melting points because of that. That's why a lot of those early organic guys that are alkanes, they're gases. Methane, propane, butane, because they're held together within themselves by a very, very weak force. And it doesn't take a lot of convincing for them to want to go away from each other and go into the gas phase. That's also, as we talked about, why a lot of organic compounds, especially nonpolar ones, are very volatile. They can go from the liquid phase into the gas phase super easy because they're not held together by really strong forces. And again, hydrogen bond is the strongest intermolecular force you could probably have. And because alcohols can do that, they typically are the winner in terms of boiling points and melting points. So if you ever have a choice of like which one should have the higher melting point or boiling point, and you see an alcohol that can hydrogen bond, that's probably going to be your winner in most cases. There's only one thing that can beat it, as we'll talk about a little bit later on. Now, in terms of phenols, they also are going to be slightly soluble in water. And again, they will kind of do a Bronsted-Lowry sort of reaction. They're going to send this hydrogen over, and this will sort of act obviously as an acid, and this will sort of act as the base, and it will form this sort of ion that is formed that we're not too concerned about in here, but that's sort of it. So it also will be slightly soluble in water. It runs into a little bit of a problem because it has that benzene ring on it, which is relatively big, but it's sort of flat. So it is semi-soluble in water, but the kind of benzene ring doesn't make it super soluble in water because it's, again, a 6-carbon ring, basically, of carbons and hydrogens. All right, so for each of these, would we expect each of them to be soluble in water? Will the first one be soluble in water? It will not. It does have a polar group, but the problem with that is this non-polar part of it, right, is pretty big. So that's going to probably be insoluble in water. How about the second one? Second one is, again, we have the OH group, and we only got a couple of carbons there, and that should make it pretty soluble. Again, when we get up to this size here on the first one, that part's just too big and gets in the way of it working well with water. Any questions on that there? All right, the next thing we're going to talk about are a couple of more organic guys, which are aldehydes and ketones. So our functional groups here for the aldehyde is the carbon-oxygen double bond with the hydrogen. And for our ketones, as I mentioned before, it is the 3 carbons in a row. And on that center carbon, you will have the double bonded oxygen there. We obviously saw earlier in this chapter how we can make each of these, right? We can make an aldehyde from the oxidation of a primary alcohol. If you oxidize a primary alcohol, you get an aldehyde. And we can make a ketone through the oxidation of a secondary alcohol. Again, if we oxidize a secondary alcohol, we will end up with a ketone. So that is how we could get to each of those sort of organic groups through the oxidation of alcohols. And as we talked about, if you start with the aldehyde or ketone, you could take them back to the alcohol by doing the reduction reaction that we saw earlier. Now, aldehydes and ketones share what is known as a carbonyl group, and that is the carbon-oxygen double bond, is the carbonyl group. This is also sometimes referred to as the carbonyl carbon. That group, that carbon-oxygen double bond, is actually a polar group. They are not sharing electrons equally here. The oxygen here is more negative. The carbon is actually more positive in that bond. So that gives it some properties that's important, and also why when we put the hydrogen back on, they go to that area as well. Aldehydes will have the carbonyl group attached to a hydrogen. Now, one of the consequences of the aldehyde is it has this functional group. And because it has that hydrogen that is attached to the carbon, as we know, hydrogen cannot have more than 2 electrons, which means this functional group will always has to be at the end of the molecule, whichever end it is, one end or the other. It has to be at the end of the molecule. And that is because it has that hydrogen. And it cannot be anywhere else because you put the hydrogen in the middle, then it has too many electrons and bonds to it. Now, just like that, though, the ketone, because it does have a 3-carbon run, the ketone, because of that 3-carbon run, that double bonded oxygen or that carbonyl oxygen or carbonyl carbon will always be never at the end. It's because it's got to at least be one in from the end to be in the middle of a 3-carbon run. So the carbonyl carbon for the aldehyde will always be at the end because it's attached to a hydrogen. And the carbonyl group there on a ketone will never be at the end because, again, it needs that 3-carbon run. So you got to go at least one in from the end for it to work out correctly. Now, how do we draw these? Again, we draw them sort of like normal. If we have a aldehyde group, we can draw the line structure with the carbon-oxygen double bond. But it's really important if you are drawing an aldehyde sort of in line structure, you do need to write the hydrogen there. Yeah? Because if I did not write the hydrogen there, what would that imply is at the end there? A carbon, right? And that is not what we have going on here. So if you are going to kind of do line structure, you do need to actually write the hydrogen in. Probably one of the few times you write a hydrogen in when you're doing sort of line structure, but you need to put it in there so people know it's a hydrogen rather than another carbon that would be at the end of it. If you're doing a ketone, same idea. All you're going to do is something like that, and that would be, again, your 1, 2, 3-carbon run with your double bonded oxygen there on the in the middle carbon of that 3-carbon run. And obviously, there are some abbreviations in terms of condensed formula that you sometimes will see. Sometimes you'll see people write CHO and they're representing the aldehyde group in sort of a condensed formula. And sometimes you'll just see that CO. I'll be honest with you, most people, even if they're writing it sort of in condensed formula, will still sort of draw out the functional group usually. So, most people would probably, still do this. Whoops, put my H in there. we'll still sort of draw it out. Even the aldehyde, and then just kind of draw it like this, rather than do that. So it's acceptable to do it that way with the circle there. But I would say most people will still just kind of just draw out that functional part of it and kind of do the rest in a more of a condensed sort of formula. Any questions on that there? So let's talk about naming aldehydes. So to name aldehydes, we touched upon it a little bit, kind of similar to alcohols, except we lay up an Al at the end. So we do an Al at the end for an aldehyde. Again, you can remember it starts with an Al, so it ends with an Al here. Now, there are some common names that are used still today. So if I had something like this, this is a 1 carbon. This is my aldehyde group. This is going to be methanal, Al. This is also sometimes referred to as formaldehyde, which you might be familiar with maybe in biology. And that's a common name, obviously, that is still used today. So you should have that familiarity of methanol and formaldehyde are the same thing. Um, if we have 2 carbons happening, instead of ethane, this is going to be ethanal, Al at the end of it. Now, with aldehydes, unlike alcohols, double bonds and triple bonds, you do not need to give the location where the carbon oxygen double bond is because it's always at the end. So it is always at the end. So you do not need to say, like, 1 ethanol or anything like that because it should always be at the end. Now, the importance of that is if we had something like this where something like that maybe. Now, in this case, we have still 3 carbons, right? So that's going to be based off of propane. This is our aldehyde group right there. So this is now going to be propanal. Now, we don't need to give the location of where this is because it's always going to be carbon 1. But what that means is when you are numbering the chain for any other groups that are there, this always has to be carbon number 1. So wherever that carbonyl carbon is, needs to be carbon number 1. So that's going to be carbon number 1 and a carbon number 2 where we have our bromine. And this would give us a 2-bromol propanal and stuff. So although we don't need to give the location of that carbonyl group or carbon, it is number 1 always in terms of numbering any other groups that may be attached there. Any questions on that there? All right, we're going to continue on here. Any questions so far on aldehydes and naming? All right, so like I said, there are some, obviously you can see some other sort of common names here for some other ones. We're not going to really use common names for aldehydes. We are going to use the more IUPAC name, that is the Al. The one common name, like I said before, you should be familiar with because books still like to use it, is formaldehyde, which is methanol, because that will still sort of pop up. So as we talked about here, we don't need to give the numbering of that carbon-oxygen double bond, but it is definitely going to always be carbon number 1 for numbering purposes of other things. And obviously you always number there. And like we talked about, we'll always have this group at the end of the molecule because of that hydrogen. It can never be inside. So you can never have it inside. It's got to be at one end or the other for it to be correct. All right, so okay, so we are obviously in this case always looking for the longest carbon chain that contains really the functional group. And hopefully you can see obviously our aldehyde group right there. And again, we want to count our carbons. So coming all the way across here, that's going to be 1, 2, 3, 4, 5. Looks like the longest. So 5 carbons is going to be based off of pentane because it's an aldehyde, pentanal. We do have a methyl group hanging off of it there. And once again, this will always be carbon number one where that carbon oxygen double bond's at, which means since that is carbon one, that would be carbon two, and that is where our methyl group would be. So two, bless you, two methyl pentanal. Yeah. Any questions on that there? Okay. So let's talk a little bit about ketones and how we name ketones. So we do use the IUPAC way of naming, and ketones end in ONE, and that is how we end ketone names. So we drop the E off of the alkane name, and it becomes ONE. The simplest ketone you could have has to have three carbons, right? Because a ketone has to have three carbons in a row. So you cannot have a one carbon ketone or a two carbon ketone because you need three carbons in a row for it to be a ketone. So that's the simplest one you could have. That is based off of three carbons, which is propane, and this would then be propanone, ONE at the end of it. Um, Again, there are some common names for ketones. We're not going to worry too much about it. You do need to, in certain cases, right around probably about four or more carbons, you do have to actually give the location of where the carbon oxygen double bond is. So, right around there, you do have to do it very similar to what we do with alcohols or double bonds or triple bonds. You have to give kind of the number on the carbon of where that carbon oxygen double bond is located. Once you get to about at least four or five carbons or more, we do want to give it the smallest number when we do that. Uh, we can see here on the bottom, we have a cyclohexane ring with a carbon oxygen double bond. And this is our ketone part right here, 1, 2, and 3 with the double bond in the middle. That is based off of cyclohexane, and this would be cyclohexanone. And the one on the bottom there does have a methyl group there. So once again here in a ring structure, we don't have to give the location of that carbon oxygen double bond, but it will definitely be carbon number one. And then if we go 2 and 3, we'll give that methyl group the smaller number. And that is again how we get to our 3-methyl cyclohexanone. Um, as you can see here, we got we have five carbons in this case, and we do need to give the location of the carbon oxygen double bond. So this is 1, 2, 3, 4, 5. That is where our pentane part comes from. ONE because it is a ketone. And once again, the ketone part is right there. Three carbons in a row with the double bonded oxygen in the middle. And the 3 is where the carbon oxygen double bond is located. So this is 1, 2, and 3. Or you can go the other way and it'll end up at 3 as well. So this is 3-pentanone. This is butanone, which is 4 carbons. And again, here we don't actually need the number here with butanone because really wherever that oxygen double bond is located, if you put it there, you put it on the other one, it's going to be number 2 no matter what you do to it. So this is butanone. You could also see here that there is some common names, and common names for ketones is like what we did with ethers. You kind of go to the left, you go to the right and see what's there. So you kind of put your, like we box the oxygen there in ethers, you box that carbon oxygen, and that's a methyl methyl. And this common name is dimethyl ketone, which is also known as propanone, also known as acetone, right? Like nail polish remover, really smelly, always opened up in a car, a closed car to see what happens in that case. Here we have our carbon oxygen double bond methyl group, ethyl methyl ketone. So here, though, when we name it here, we are going to go with the IUPAC name, but again, the common name here is very similar to how we did the common name for ethers in terms of how we do it. Even here, when we have two of the same group, ethyl, ethyl, so common name for that, diethyl ketone in this case. Any questions on that there? All right, so give the a look, and again, for our ketone, 1 carbon, 2 carbons, 3 carbons, and the carbon-oxygen double bond. So that is our ketone functional group right there. Now we want to obviously find the longest carbon chain that includes that functional group, and you could go actually straight across here. We'll do it. You could also, if you want to, go straight across and go down. It's up to you. But here, they're both going to give you, looks like 1, 2, 3, 4, and 5 carbons. So 5 carbons is based off of pentane. We're going to drop the E and put ONE at the end, and that's going to be pentanone. Do I need to give the location of the carbon-oxygen double bond in this case? I do in this case because it's 5 or more carbons. So at that point, you do. We want to give the carbon-oxygen double bond the smaller number. So you could probably just see if you go right to left here, that will definitely give the carbon-oxygen bond there the smaller number. So this is going to be 2-pentanone for the location of that carbon-oxygen double bond. And once again, with ketones, 5 or more, you need to kind of put that number in there. Again, like we do with alcohols, double bonds or triple bonds. At that point, because we locked in the numbering, we do have one group hanging out there, and that's a methyl group, and that's at carbon number 4. So that's going to be a 4-methyl 2-pentanone. Yeah, so 4-methyl 2-pentanone. Any questions on that one there? Let's talk a little about aldehydes and ketones and in water. So aldehydes and ketones can form hydrogen bond with water, and it's between the carbonyl oxygen and the hydrogen of the water. So aldehydes and ketones again have this carbonyl group, which is a polar group, oxygen more negative, carbon more positive. So when water rolls through with its negative and positive, it can do some hydrogen bonding there between water and that carbonyl group. It cannot hydrogen bond with itself, so aldehydes and ketones cannot hydrogen bond with itself, but it can hydrogen bond with water, which makes it fairly soluble. Kind of like our normal sort of rule on solubility, the more carbons you have on there, the less soluble it's going to be. So basically, if we have 4 or less carbons, you're going to be okay in terms of solubility. But again, if you kind of are greater than that in terms of how many carbons there is, for the same reasons, you now just have a bigger non-polar part that gets in the way of the polar part, they're not going to be very soluble in each other. So 4 or less, you're going to be good with these guys. But more than that, you're going to start to get some slightly soluble and insoluble that's happening here with our aldehydes and our ketones in this case. So lower number of carbons allows the water to get in there next to the carbon oxygen double bond on the aldehyde and ketone and allows it to hydrogen bond and become soluble in each other. Acetone, as I mentioned before, is propanone. Again, it's used in nail polish remover, also cleaning fluids and paints. Formaldehyde, as we talked about before, is methanol, which is again an aldehyde used to preserve their organic or biology a lot. Now, some aldehydes and ketones are used as flavoring and stuff like that. So, benzyl aldehyde is a benzene ring with an aldehyde group, and you may notice that the aldehyde group is actually off of the ring. Yeah, it's kind of attached like a group, and that is known as benzyl aldehyde, and that is basically kind of your major part of what almonds are. Here again, vanilla, we have our aldehyde group there, and here with cinnamon, we have our ketone group hanging off of there as well. So some of these are important in some food, and some smells and flavoring that we see. All right, so classify each of these as an aldehyde or a ketone. All right, so let's take a look. Taking a look at the first one here, I got 3 carbons in a row. And on that center carbon, I have my double bonded oxygen. So that definitely is a ketone that's happening. Here on the right, on B, I got a carbon oxygen double bond with a hydrogen. And again, that is an aldehyde. Same thing over here, carbon oxygen double bond with a hydrogen at the end. Also going to be an aldehyde. And this last one is it is a ketone. Once again, that's a carbon, that is a carbon, and that is a carbon. So this top part of the ring here is our ketone group, and this would be our ketone. Any questions on that there? All right, let's take a look at some of these here. Why don't you give the names of these ketones? Why don't you also give the name of this guy? Why don't you also draw? Let's go with go with 4-methyl 2-hexanone. You also draw 3-bromol butanol. It looks like 1, 2, 3, 4, 5, and 6. So that's going to be hexanone, O-N-E. Once again here, there's really nothing else attached since that is all part of the group. We do need to give the location of the carbon-oxygen double bond here because it's 5 or more. And it looks like if we go right to left there, that's going to give us a 2-hexanone. Any questions on that one there? Bottom one, also a ketone right there, 3 carbons in a row with our carbon oxygen double bond in the middle carbon. Longest carbon chain with it, 1 carbon, 2 carbons, 3 carbons, and only 4 carbons, as that is a chlorine. Yes, that is different. So that is 4 carbons, which means that is butane. And that would then be butanone. I'll spit that out right. So butanone. Here, we don't have to give the location because it would end up at carbon number 2 no matter which way you go. But we will go 1 and 2, and then that's going to be 3 and 4. So that is the location of where our chlorine's at, carbon number 4. That's going to give us a 4-chloral butanone. Any questions on that one there? Yeah. Why do we not need to give a location here? It's because really for ketones has to give it at 5 or more, and that's because, for example, we just look at the carbons. So we basically had 4 carbons, right? And the way it's drawn, it was there, right? The only other place that that carbon oxygen double bond could have been in this sort of picture would have been over here, right? And if I were to number it, the top one, this would give me 1 and 2 for that location. But if I was doing the bottom one, I would end up at 1 and 2. It's basically the same at that point. So it's not until you get 5 or more, like we did up here, that you do get multiple locations of where it could be with some different numbers. So for ketones, 5 or more, you got to kind of give that number. Yeah. Other questions? Yeah. The four is actually, yeah, the location of where the chlorine is on which carbon in that longest carbon chain. Says carbon number four is where you find the chlorine. Other questions? Okay. So coming up here, this is the aldehyde group you could hopefully see. And if we count it up, 1, 2, 3, 4, 5, and 6, remember that that is a hydrogen, so not a carbon. So 6, that's an aldehyde, is going to be hexanal, Al at the end of it. Once again, we do not need to give the location of the carbon oxygen double bond ever in an aldehyde because it's always going to be at the end. But for numbering other things, which we have a chlorine here, that wherever that carbon oxygen double bond is located, whichever side, it should always be carbon number one. So that's going to be carbon number one, carbon number two, carbon number three, and carbon number four. So that's going to get us a 4-chloral hexanal in this case. Yeah. Any questions on that there? All right, so to draw, we're going to go backwards here. So ONE does tell us it's a ketone, which means we should have 3 carbons in a row at some point with a double bonded oxygen in there. We're going to build that off of hexane, which is 6 carbons. So I'll go here maybe. 1, 2, 3, 4, 5, and 6, I think. So 2 is where the carbon oxygen double bond is located. And once again, since you are drawing, you could choose either way. I'm going to choose that as my carbon number 2, which means for me, my carbon number 1 is right there, right? And that takes care of this part of the name. Because I have to lock in this way of numbering, that's 1, 2, 3. This would has to be carbon number 4 for me. And that is where a methyl group would be. And maybe I'll just squeeze it in right there. And that's going to take care of that. Just like anything else, we're now just going to hydrogen it up, right, to give everybody 4 bonds. So we'll need 3 there. We'll need 2 there. Just 1 there. 2 there. None here at carbon number 2 because it already has 4 bonds. And 3 hydrogens there at carbon number 1. Yeah. Any questions on that? Again, if you're going to do like a line structure type of deal, you would just start with the 6. Well, 1, 2, 3, 4, 5, and 6. Again, you would put your double bonded oxygen on carbon number 2. And at number 4, you would put a line, right, going up there. And it looks something like that up there in upper left. Any questions on that drawing there? Taking the next one here, which is 3-bromo butanal. So the Al tells me it's an aldehyde, and the butane part tells me it is 6, not 6, it is 4 carbons. So we're going to go 1, 2, 3, and 4. You can now put your aldehyde group, and once again, it's up to you. You could put it on the left or you could put it on the right. It doesn't matter since you're drawing it. I'm going to put it on the right here, and the aldehyde group should always look like that, right? So that is my aldehyde group. Because I did put my carbon oxygen double bond on the right hand side, that is definitely going to be carbon number 1 for me. Yeah, and then obviously if you put it on the other side, that would be carbon number 1 on the other side. That means for my bromine, it's going to end up at carbon number 3, which should be right about here. And now we could add in our hydrogens. So we need 2, we need 1, and we need 3 in this case. Same deal if you're doing line structure, 1, 2, 3, and 4. And again, we're going to put our double bond and actually draw our hydrogen in, right? And that maintains our 1, 2, 3, and 4 carbons, right? So again, if you don't put the hydrogen in, just leave it as a line. You have too many carbons technically. And for this case, 1, 2, 3 would be right here, and we put a bromine in there. Yeah. Any questions on drawing those there? Yeah. Say again. What is it? start numbering at the double bonds, they're asking. So in the case of an aldehyde, you always start here as number one. So wherever the carbon-oxygen double bond is going to be number one for the aldehyde. And because it's an aldehyde, it will either be at one end or the other. So that carbon where it's at will either be basically at one end or the other. For a ketone, it could be anywhere, kind of, in a sense, depending on how many carbons you got. But you do want to give the carbon-oxygen double bond the smaller number. So like this one up here that we drew, if we just counted the carbons, we got 1, 2, 3, 4, 5, and 6 carbons basically on that guy up here on top. And if we wanted to number this carbon, which has the carbon-oxygen double bond, we would go left to right here because that would then give it a carbon number 2. As opposed to if we started over here, we wouldn't get there until we got to like carbon number 5, right, which is a larger number. So we would want to give that guy the smaller number. And once you lock the number in place for that guy, anything else is numbered with the same number that's there. Other questions? All right, so we touched upon this as we went through it, so we're not going to kind of go through these obviously again because we talked about dehydration of alcohols. We obviously talked about the oxidation of alcohols. We talked about that. We talked about the oxidation of thiols. That was the disulfide bridge. So the next thing we're going to talk about is two sort of tests that are used for the oxidation of an aldehyde. And we typically will use these tests to distinguish between did we start with a aldehyde or did we start with a ketone, for example. One test is what is known as the Tollens test, and the Tollens test is a reagent that contains silver, and the silver gets oxidized, or the silver will oxidize the ketone. I'm sorry, I say this right. The silver will oxidize the aldehyde, but not the ketone. That's what I'm trying to spit out there. And what happens is the silver actually gets reduced to solid silver, and it ends up looking a positive test like a mirror, sort of really silvery here. And that's why it's sometimes referred to as a mirror test. So what happens is if you take an aldehyde, such as what we have in this equation here, we have our aldehyde. This silver gets reduced. The aldehyde gets oxidized. And we know what we get when we oxidize an aldehyde, right? We get a carboxylic acid. So remember that this oxidation is the kind of second oxidation that we talked about as we go from a primary alcohol to an aldehyde, and then you oxidize it one more time. The oxidation involves basically just popping a oxygen right in there. The result of that is you make this thing, which is a carboxylic acid. The functional group of a carboxylic acid is sometimes abbreviated as COOH. It is what I boxed in there. If you see that COOH, it means that group right there, carbon-oxygen double bond with an OH. By the way, to name a carboxylic acid, which we might have touched upon last time, we basically ended in oic acid. So instead of ethane, because there are two carbons and it has a carboxylic acid, we drop the E off of ethane and put oic acid at it, and that's known as ethanoic acid. It's also acetic acid, the major component in vinegar. This is a positive test for an aldehyde being oxidized, is this Tollens test. Remember that when we take our secondary alcohol and we oxidize it, we do lose this and we lose this, and we end up with our ketone as we talked about. And remember that if you try to oxidize this one more time, nothing's going to happen. Yeah. So remember for our aldehyde, we're starting with our primary alcohol that gets oxidized to the aldehyde and then gets oxidized one more time. So If you're not sure what you're starting with and you do this test and you end up with a positive test, it's pretty safe to assume you started with a aldehyde because that's the only thing that should happen and not a ketone. If you do this test and it's a negative for it, then perhaps you started with a ketone because it will not go through this oxidation. Now, the test that you'll use in lab is the Benedict's test, which you probably used before when you did the little dialysis bag and you pop that thing open at some point, maybe. The Benedict's test uses copper, and it basically reduces copper, and it will oxidize again a aldehyde to a carboxylic acid. So if we take a look at here, we have our aldehyde, and again, that's going to have this group on it. And once again, it's going to oxidize it to our carboxylic acid, which will end in oic acid, right? Carboxylic acid. And a positive test here will be, I don't know, kind of like a gross looking orangey type color, reddish color, probably, maybe. They say red, but a lot of times you see it orangey. And that's because copper 2 is blue. And then when it gets down here to copper 1, it is actually that orangey red color. And again here, Benedict's test is used as a positive test for the oxidation of an aldehyde to a carboxylic acid, but not a ketone. Same deal. The ketone will not get oxidized. So if you run this test and you get a negative test for Benedict's reagent, that means that you probably started, in your case of your lab, with a ketone. And if you run this test and you get a positive test, you probably started with an aldehyde. So again, this test is used for that. I think in your lab you might do an additional test to verify a ketone with some iodine, but this is the one you could use to verify that you started with an aldehyde. So if you get a positive test here, which is what you see here, positive test would indicate that you started with an aldehyde and you made a carboxylic acid. This is actually glucose, and it makes a carboxylic acid from it here. And again, going from our aldehyde to our carboxylic acid in this case. Yeah. Once again, ketones will not do that. Any questions on Tollens test or the Benedict's test? Yeah. Okay. Now, we talked about the reduction of aldehydes and ketones at the end last time. And remember that that reduction reaction is how we get back to our alcohols that we started with. So really, when we're talking about our aldehydes and ketones, they are originating from our primary alcohol that you oxidize to a aldehyde that you oxidize to a carboxylic acid. So you're going from a OH to an aldehyde to a carboxylic acid in this case. And again, if you started with a secondary alcohol, going from an OH, you're going to oxidize it to a ketone, which is our 3-carbon run with the oxygen in the middle in this case. The reduction reaction is what we went over at the end last time, where we put basically the hydrogen back on in this case. Well, I guess you think of it as losing the oxygen in this case, minus the oxygen. And here we're putting the hydrogen back on. So again, the reduction reaction is basically the reverse that takes us back to an alcohol, either primary or secondary alcohol, depending on what you're starting with. If you're starting with an aldehyde and you add, again, some hydrogen, you had just a very simple aldehyde, as we talked about last time, and you do the reduction reaction. Remember, it is this double bond that becomes a single bond. And one H to the oxygen and one H there. And now we have our primary alcohol back in this case. And the same thing works with a ketone. If you had a simple ketone such as this, and you added that hydrogen, which would reduce it back. Once again, this becomes a single bond, like we talked about last time. And again, hydrogen to here, hydrogen to there. We get back our secondary alcohol in this case. So again, the reduction is basically the opposite of the oxidation reaction of the alcohols. And you could kind of undo it by putting hydrogen back in and going the other way. Any questions on that there? All right, we're going to lay that up